Hello students, welcome back to the class of chemistry. In the previous class, we discussed that to explain the chemical bonding, two theories were proposed based on quantum mechanical model of atom, valence bond theory and molecular orbital theory. In the last class, we discussed about valence bond theory in detail, but VBT has some limitations like it fails to explain the formation of coordinate covalent bonds. This theory fails to explain the magnetic properties of oxygen molecules. It does not explain the bonding in electron deficient molecules such as diborane. So, now in today's class, we are going to discuss about molecular orbital theory. But before starting the today's class, I would like to share some learning objectives, and these are: describe the molecular orbital theory of homonuclear diatomic molecules. Second is write electronic configuration of molecules, and third is explain stability of molecules and explain the concept of hydrogen bond. Dear children, now we move on molecular orbital theory. The molecular orbital theory is a theory of chemical bonding developed by F. Hunt and R. S. Mulliken to describe the structure and properties of different molecules. The valence bond theory failed to adequately explain how certain molecules contain two or more equivalent bonds whose bond order lie between that of a single bond and that of a double bond, such as the bond in resonance stabilized molecules. This is where the molecular orbital theory proved to be more powerful than the valence bond theory. The molecular orbital theory states that atomic orbitals of each atom tend to combine together and form molecular orbitals. The main points of this theory are: first is the electron in a molecules are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. Second is the atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Dear children, third is while an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. Fourth is the number of molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital while the other is called antibonding molecular orbital. The fifth one is the bonding molecular orbital has lower energy and hence greater stability than the corresponding antibonding molecular orbital. Sixth is just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. Dear children, the seventh point is the molecular orbitals like atomic orbitals are filled in accordance with the above principle, obeying the Pauli's exclusion principle and the Hund's rule. However, to understand the molecular orbital theory more clearly and in depth, it is important to understand how molecular orbitals are formed. Molecular orbitals are formed by linear combination of atomic orbital, that is L, CaO. Dear students, as you all know, according to wave mechanics, the atomic orbitals can be expressed by wave functions, that is psi, which represent the amplitude of the electron waves. These are obtained from the solution of Schrödinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals which are one electron wave function for molecules are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbitals has been adopted. Now, let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in 1s orbital. The atomic orbitals of these atoms may be represented by the wave functions psi A and psi B. Dear students, mathematically the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals as shown, that is psi MO is equivalent to psi A plus minus psi B. Therefore, the two molecular orbitals sigma and sigma star are formed as sigma is equivalent to psi A plus psi B and sigma star is equivalent to psi A minus psi B. The molecular orbital sigma formed by the addition of atomic orbitals is called the bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of atomic orbital is called anti-bonding molecular orbital as depicted in the picture. Qualitatively, the formation of molecular orbitals can be understood in terms of the constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atom reinforce each other due to constructive interference, while in the formation of anti-bonding molecular orbital, the electron waves cancel each other due to destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of the bonded atoms, because of which the repulsion between the nuclei is very less. While in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is a nodal plane on which the electron density is 0, that is called nodal plane between the nuclei, and hence the repulsion between the nuclei is high. Electrons placed in a bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. Therefore, a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. In contrast, the electron placed in the antibonding molecular orbital destabilize the molecule. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. It may be noted that the energy of the antibonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital has been lowered than the parent orbitals. The total energy of two molecular orbitals, however, remain the same as that of two original atomic orbitals. Now the question is, can all atomic orbitals combine to form molecular orbitals? The answer is no. There are certain conditions for the combination of atomic orbitals. And what are these? The linear combination of atomic orbital, molecular orbital takes place only if the following conditions are satisfied. The condition is the combining atomic orbital must have the same or nearly the same energy. This means that one s orbital can combine with another 1s orbital, but not with 2s orbital, because the energy of 2s orbital is appreciably higher than that of 1s orbital. This is not true if the atoms are very different. Okay. Second point, the combining atomic orbital must have the same symmetry about the molecular axis. By convention, z axis is taken as the molecular axis. It is important to note that atomic orbitals having same or nearly the same energy will not combine if they do not have the same symmetry. For example, 2pz orbital of one atom can combine with 2pz orbital of the other atom, but not with the 2px or 2py orbitals because of their different symmetries. Third one is, the combining atomic orbitals must overlap to maximum extent. Greater the extent of overlap, the greater will be the electron density between the nuclei of a molecular orbital. Dear children, types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, delta, etc. Energy level diagram for molecular orbitals are as in your screen. Students, we have seen that 1s atomic orbital on two atoms form two molecular orbitals designated as sigma 1s and sigma star 1s. In the same manner, the 2s and 2p atomic orbitals, 8 atomic orbitals on two atoms give rise to the following 8 molecular orbitals. Antibonding molecular orbitals sigma star 2s, sigma star 2pz, pi star 2px, pi star 2py. Bonding molecular orbitals are sigma 2s, sigma 2pz, pi 2px and pi 2py. The energy level of these molecular orbitals have been determined experimentally from spectroscopic data for homonuclear diatomic molecules of second row elements of the periodic table. The increasing order of energies of various molecular orbitals for oxygen and fluorine is given, which you can see, that is sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz and pi 2px is equivalent to pi 2py, and it is lower than the pi star 2px and equivalent to pi star 2py, and it is of course lower than sigma star 2pz. However, the sequence of energy levels of molecular orbital is not correct for the remaining molecules like Li2, Be2, B2, C2 and N2. For instance, it has been observed experimentally that for molecules such as B2, C2 and N2 etc., the increasing order of energies of various molecular orbital is sigma 1s, that is lower than sigma star 1s, and this is lower than sigma 2s, then sigma star 2s, then pi 2px and that is equivalent to pi 2py, and sigma 2pz, and it is lower than pi star 2px equivalent to pi star 2py, and it is lower than sigma star 2pz. The important characteristic feature of this order is that the energy of 2pz molecular orbital is higher than that of 2px and 2py molecular orbitals. Electronic configuration and molecular behavior, the distribution of electrons among various molecular orbital is called the electronic configuration of the molecules. Now students, can you tell what information can we get from electronic configuration of the molecule? From the electronic configuration of the molecule, it is possible to get important information about the molecule like stability of the molecules, bond order, bond length and magnetic nature. Now dear students, how can we calculate the stability of molecules? If Nb is the number of electrons occupying bonding orbitals and Na the number of electrons occupying the antibonding orbitals, then the molecule is stable if Nb is greater than Na, and the molecule is unstable if Nb is less than Na, and bond order is 1 half the difference between the number of electrons present in the bonding and the antibonding orbitals, that is bond order is equal to half Nb minus Na. Bond order values of 1, 2 or 3 represent single, double or triple bonds between two bonded atoms respectively. Bond length. Dear children, the bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Magnetic nature, if all the molecular orbitals in a molecule are doubly occupied, the substance is called diamagnetic, repelled by magnetic field. However, if one or more molecular orbitals are singly occupied, it is paramagnetic, attracted by magnetic field. Example, oxygen molecule. Now let us come to bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic molecules like H2, He2 and O2. Hydrogen molecule. Dear children, it is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in 1s orbital. Therefore, in all there are two electrons in hydrogen molecules which are present in sigma 1s molecular orbital. So, electronic configuration of hydrogen molecule is sigma 1s square. The bond order of hydrogen molecule can be calculated as given here. Bond order, the formula is half 2 minus 0 and that will be equal to 1. This means that the two hydrogen atoms are bonded together by a single covalent bond. Since no unpaired electrons is present in hydrogen molecule, therefore it is diamagnetic. Dear children, now we move on another molecule, that is helium, He2. The electronic configuration of helium atom is 1s square. Each helium atom contains 2 electrons. Therefore, in He2 molecule, there would be 4 electrons. These electrons will be accommodated in sigma 1s and sigma star 1s molecular orbitals, leading to electronic configuration. What is that? He2 is equal to sigma 1s square and sigma star 1s square. What is the bond order? That is half 2 minus 2 is equal to 0. It means He2, it means helium molecule is therefore unstable and does not exist. Now, the another example is oxygen molecule. The electronic configuration of oxygen atom is 1s square, 2s square, 2p4. Each oxygen atom has 8 electrons. Hence, in O2 molecules, there are 16 electrons. The electronic configuration of O2 molecule therefore is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2 and pi 2px square equivalent to pi 2py square, pi star 2px1 equivalent to pi star 2py1. From the electronic configuration of oxygen molecule, it is clear that 10 electrons are present in bonding molecular orbitals and 6 electrons are present in anti-bonding molecular orbitals. Its bond order therefore is half Nb minus Na, half, and how many number of electrons present in bonding, that is 10, and how many electrons are present in anti-bonding, that is 6. So, bond order will be 2. So, in oxygen molecule, atoms are held by a double bond. Moreover, it may be noted that it contains 2 unpaired electron in pi star 2px and pi star 2py molecular orbitals. Therefore, oxygen molecules should be paramagnetic. In this way, the theory successfully explains the paramagnetic nature of oxygen. Similarly, the electronic configuration of other homonuclear diatomic molecules of the second row of the periodic table can be written. Hydrogen bonding. Dear students, as you all know, nitrogen, oxygen and fluorine are highly electronegative elements. When they are attached to a hydrogen atom to form covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atom, and this partially positively charged hydrogen atom form a bond with the other more electronegative atom. This bond is known as hydrogen bond. It is weaker than the covalent bond. For example, in HF molecule, the hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another molecule as depicted in the slide. Hydrogen bond acts as a bridge between two atoms which holds one atom by covalent bond and the other by hydrogen bond. Hydrogen bond is represented by a dotted line, while a solid line represents the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom like F, O or N. Phon means fluorine, oxygen and nitrogen of another molecule. Dear children, now we move on the types of hydrogen bond. There are two types of hydrogen bond. First is intermolecular hydrogen bond and another is intramolecular hydrogen bond. First is intermolecular hydrogen bond. It is formed between two different molecules of the same or different compounds. For example, hydrogen bond in case of HF molecule, alcohol or water molecules, etc. Second, intramolecular hydrogen bond. It is formed when hydrogen atom is in between the two highly electronegative like fluorine, oxygen and nitrogen atoms present within the same molecule. For example, in ortho-nitrophenol, the hydrogen is in between the two oxygen atoms. Now, take a quick look on the main points which we discussed in today's class. The molecular orbital theory states that atomic orbitals of atoms combine together and form molecular orbitals during chemical bonding to form molecule. Molecular orbitals are formed by linear combination of atomic orbitals. The number of molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is called anti-bonding molecular orbital. Fourth is the bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. The formula of bond order, that is half the number of electron in bonding and the number of electrons present in anti-bonding orbital. More the bond order, more is the stability of the molecule. Sixth is, the molecule is stable if Nb is more than Na, and molecule is unstable if Nb is less than Na. If all the molecular orbital in a molecule are doubly occupied, the substance is dimagnetic, and if one or more molecular orbital are singly occupied, it is paramagnetic. Eighth is, hydrogen bond is the attractive force which binds hydrogen atom of one molecule with the electronegative atom like fluorine, oxygen or nitrogen of another molecule. Dear children, some questions for you, and these are: first is, on the basis of molecular orbital theory, explain why the helium molecule does not exist. Second question is, compare the relative stability of the following species and indicate their magnetic properties, that is oxygen O2, second O2 plus, and third is O2 minus charge. Third question is, give reasons why. First is, water has high boiling point. Second is, ammonia gas is soluble in water. Next is, out of O-nitrophenol and para-nitrophenol, which is more volatile and why? Fifth question is, what is the difference between bonding and anti-bonding molecular orbital? Dear children, thank you and have a nice day.